All right, welcome back. So this is a second method of how to solve uh, problem 2. So this is method 2. So this is, I left this part from the first method where we went and found the our Thevenin. That process stays exactly the same. So if you want to watch the full worked out solution for our Thevenin, make sure just to go back to the method 1 video for problem 2, and you can see how that's worked out. But just look at your dependent sources, zero them out, work left to right, find our equivalents, and there we go. So that process is the same. Okay. But our new process for our new method still requires us to redraw our circuits. So just everything the way it was. 25. This will be 15. This is 1 amp. And this is plus minus VOC. Okay. So whereas before we went and found in the method 1 video, we went and found this voltage here, and we used the parallel voltage concept to find the Thevenin. For this method, what we're going to do is, if we want to just directly find this current, so this current, which remember we called I short circuit, which is the same thing as I Norton, if we wanted to directly find it, we could take our original circuit and drop our wire on there. And then now what we can do is we'll look at how these currents meet up from this two sources and what they produce. So let's look at this battery. So if we were to come up through here, this current would leave here, travel through this resistor, then hit right here. So we're looking at this node. Okay, so this node, it has an option. It can either go down this way, where there's 25 ohm resistance, or it can travel down this wire all the way. See, I don't know if you can see that. Or you can travel down this wire all the way around and end up back where it started with zero resistance. The current is going to follow the path of least resistance, so it's going to take this route. So now we can say that this current, whatever this current is right here, will be this current and then this current, and it'll continue and hit this node here, where 1 amp will meet up with whatever that current is, and they'll combine to create the I short circuit, which is just the I Norton. So how do we find this I? Well, what we'll do is I'm going to use green here just because I've used yellow so much. Let's do a big KVL. So we're going to walk this loop. So if I can walk a closed continuous loop inside there, what I'll do is whatever terminal I hit, that's this sign I'll assign to my voltage. So I'll start right there at the corner. I'll hit the negative terminal, the 10 volt battery, so negative 10. Then I'll keep travel up through that way. I'll hit the positive terminal of that 15 ohm resistor. Then I'll keep traveling that way, until I end up back where I started. And I don't hit anything else, so I can just close it off and equal it to 0. Okay, so here, VR15 is equal to 10 volts. Okay. So now what I can do is, if I know that I lose 10 volts to that 15 ohm resistor, I know that I can find from V is equal to IR, I can find I is equal to V over R, which will be 10 volts over 15 ohms. And that should be 0.67 amps. So that I is 0.67 amps. 0.67 amps. So if we know that 0.67 comes in, hits that node, we know 1 amp comes up and hits this node. We know that I Norton equal to I short circuit is leaving. We can say I Norton is equal to 0.67 plus 1, which gives 1.67 amps. And that is the same value that we got whenever we did the problem within method 1. So there's more than one way to solve this problem. Use whichever method you feel more comfortable with. Just know that there are options available. So if you can recognize this, you can use it.